So last time recall that I talked about what are cyclic groups and how the order of a subgroup divides order of a group for a finite group. And also last time at the end of the video I started talking about what are order of an element. So recall that order of an element A, which sometimes I will denote by this or by this. This is the smallest natural number such that when you operate A that many times it gives you the identity element. So yeah, so that is how we have defined order of an element inside a group. So here A is inside a group G. Now to assume order of A is finite, because it may be the case that it is not finite. For example, if you take the element 1 in the group Z plus, we have seen that this is a cyclic group generated by the element 1. So how many times uh, you can like, there is no such natural number such that whenever you add one that many times you will end up having zero, right? So that order is infinite. So yeah, so here we're assuming the order of A is finite. So now let's see how order of some power of A behaves with respect to the order. So my claim is this order of A power k becomes order of A, and if you and then you divide it by the GCD of the power that you raise k and the order of A. So that is my first claim. Even before that, let's see one thing. So suppose order of A power k is L. We already have order of A is finite, right? And so order of A power k has to be finite also, because then you may take the cyclic group generated by that element. Then you get the cardinality of H is same as this, but this is finite because G is a subgroup of a finite group, right? So yeah, uh, in fact, H is a subgroup of this group, and this is finitely many elements by your assumption. So yeah, this is finite, and so let's say suppose its order is L. So L is finite, and then you get A power K power L becomes identity firstly, and L is the smallest natural number such that A power K per that number becomes identity by definition of an order. So here you get A power KL, that is identity, right? So you get that order of A. So here you can apply Lagrange's theorem, for example, because then uh, you may take the subgroup generated by A as your bigger group, and then you can show that the scale is a multiple of order of A. So let's denote it by n for simplicity. So KL is a multiple of n, or that means n divides scale. Yeah. And so this is n, this is L. So you have to show that L is n by GCD of n and k. So now, so we already have this, and so we can see GCD of this divides k by GCD of dates time L, right? Because this follows from this directly. Because both sides we are just dividing by a fixed number, precisely GCD of n and k. But now observe one basic fact about numbers, that whenever you have two numbers, say n and k, and you each divide by their GCD, so you have these two numbers, right? So what will be their GCD? because you have taken out the largest common factor from both of the numbers, right? Which is the by definition the GCD of n and k, and you have already factored out that highest possible common factor of both numbers from them. So you end up having just one, right? Because it cannot be anything more than one because already we have factored everything that is common in between n and k. So their GCD is one, and so from these two you get that. So this is a quantity and that divides product of them, but because this quantity and this quantity are relatively prime from this, you get this quantity uh, has to divide L, right? Because this quantity cannot divide the other possible factor, so you get that this quantity has to be less than equal to L, right? And also, so this is that. And secondly, if you take a power k and then you raise it to this power, you get, you may just switch the role of k and n, right? So you get a power n power k per GCD of n and k. But that is 1 because order of a is n. So this is 1 means, sorry, that is identity. So and if you raise anything to the per identity, you will again get identity by definition. So you get that this is indeed a natural number. When you raise a power k to that assembly, you get identity. And this is the smallest of all such natural numbers by this, right? Because this quantity is always lesser than equal to any other L. So this, so by definition of order, you get order of this is precisely n by GCD of n and k. So that is important or useful formula. Yeah. So this is the first thing. Also, let's see one more small corollary of Lagrange's theorem. So you pick any element A from a group and you consider the subgroup generated by that element, right? Then you get that, so by Lagrange's theorem, order of this divides order of the group, right? And because H is cyclic group generated by A, you get order of H is same as order of A. So you get that inside any group, any element of that group must have order that is a divisor of order of the original group. So that is again a small corollary. Yeah. So now let's see. So we have seen what are cyclic groups, what are cosets, Lagrange's theorem. Uh, yeah. Or I can talk about some more on cosets. So cosets, remember, we have started, the setup was that we have a subgroup, H of a group G, and you have a coset of A, that is just these things. This is a left coset to be precise. This is left because we are taking the element A or multiplying the element A from the left, right? Uh, yeah. So, and so one thing, so this is clear, right? Whenever you have some, say, two cosets and they are same, this this will happen if and only if you get that. So let's see when this happens. So suppose this is true. So then you take the element E and you can write it as A times E, but E is in H, right? And that is same as BH. So A is in BH. That means A is of the form this because any element of BH looks like B times H for some small h. So you get that B inverse A, this is small h, so this is in H. So whenever AH and BH are same, you get B inverse A is in H. And also conversely, suppose uh, B inverse A is in H. So that means B inverse A looks like some H, and so A some BH. and this means that uh, this becomes BH. So A is in BH. So whenever you multiply any other elements H prime with A, you get B H of some H prime, right? But that is again H because we are not doing anything but just taking an element of H and again multiplying it with this set itself. So you get this is in BH. You get this, right? And also we know that both of them must have same cardinality. So you get that is same as this. Yeah, so this is a nice small application like suppose you have a bunch of cosets. So you might want to identify that which of them are like distinct cosets, like because there's no point taking same coset more than once. So you can just do it by observing the representatives of that coset and see whether uh, this relation holds or not. Yeah. So there is again a small application. So this also shows that whenever you have some h in h, then h this is same as this, right? Because of course, because h is you might think as E inverse h because this is just E times h, right? So E inverse h, which is h in h. So that is again is the application of uh, part one. Yeah. So now let's come to the main thing. So we have seen subgroups and we have also seen cyclic groups. So now we'll see how a subgroup of a cyclic group will look like. So far we have seen examples of two types of examples of cyclic groups. One of them are Z mod n. This is finite cyclic group of order n, and we have seen this infinite cyclic group of order n. Right. So we have seen two types of examples, both finite and infinite. And now let's see what are subgroups of cyclic groups. Yeah. So so let G is a cyclic group generated by this and H be a sub. So any element of G would look like some powers of A, right? So same things will hold for the elements of H. So there will be some powers of or maybe some positive. Yeah. So what I'm going to do is uh, I will take this. I will take the collection of all such say n such that a power n belongs to H, right? And I will choose the minimum of that set. And that minimum, like I can find the minimum due to the well ordering principle, because this collection is just a subset of natural numbers, bounded subset. This is a so by well ordering property or principle, I will get the smallest element of this collection. So we'll just call it K. So firstly, A power K is in H, right? That is by definition because K is the minimum of such. So you get that so you get the cyclic group generated by A power K that is in H. That is by definition of a group. So there is one. And second thing to observe that suppose you pick any other element, so that will look like something like this. And because so now by definition K cannot be more than n because K is the also smallest. So you can apply the division algorithm and you get something like this with uh, R is at least uh, at least 0 and it can be at most K minus 1 or it can write it as less than K. So you get now A power n, you can write it as A power QK times A power R. And now A power K is in H. right? So this quantity is in each, and this quantity we have chosen to be in each. So you get these two things. So you write a power r as a power n times something a power k power minus q. So both of them are in each, right? Because we are just choosing, or let me more precise, the inverse of this. So because this element is in each, its inverse will also be in each. So you get a power r is in each. But so r must be less than uh, or r is at least k, right? Because that is how you chosen k. K is also smallest power, and r is one of them. So r cannot be less than k. But there is a contradiction, right? Because here we have by division algorithm you got r is cannot be equal to or more than k, but here we have got that. So you get a contradiction. So it must be the case that r is 0. And what does it imply? It implies that n is kq. That means any arbitrary element, because this element was arbitrary, right? So any arbitrary element of H would belong to the cyclic group generated by A par Q. So you get that H is inside this cyclic group. And by 1 we have the other inclusion. So combining these two, we get H is generated by some power of A. And more importantly, H is cyclic. Yeah. And so we get that subgroup of any subgroup of any cyclic group must be cyclic. And what is its order? Its order, by Lagrange's theorem, we know its order must divide the order of the group. But here you can say more, because this order of H is order of A par K because H is cyclic. And this thing we have shown just before, that this thing is, if you take say order of A and you divide it with this GCD of order of A and K. And this all makes sense, by the way, for only finite groups. But yeah, but this result is independent of whether it is finite or not. So maybe if J is finite, J is generated by A, then these things make sense. So precisely we also uh, can figure out what is the order of that subgroup. Yeah, so that is a very important thing. Uh, so we get that this any subgroup, so any subgroup of a cyclic group is cyclic. So yeah, so that is one of the things. And so now remember, I've asked a question in one of my previous videos that by Lagrange's theorem we know that order of a subgroup must divide the order of the group, but whether the converse is true or not, that is, given any divisor of a finite group, can you find a subgroup of that order? So the question is, so I will talk about this question in later videos more generally, but here let's see, at least we can figure something out about cyclic groups. So the question is, say order of G is n, G is cyclic generated by A, and M is a divisor of n. Find, or can you find a subgroup H of G of order M? So the first thing to note is that it's enough to find an element of that order, right? Because H is generated by some element. So we know H is generated by some power of E. Let's call that power K, right? And we need we need to choose K such that, so we need order of H to be K, or sorry, order of H to be M. That is order of A power K to be M. But that is order of A by GCD of N and K. So we need to find K such that this relation holds. Yeah, that is the important thing. I will talk about these things in details in next video. But You may also try to figure out whether such a key exists or not. Or for the next question, you can ask that whether, like, if you find one subgroup, say I'm saying that there is one subgroup H for any divisor of the or divisor of n. But now the question is whether, like, how many subgroups for a particular divisor do you have? Like, suppose you have, I'm saying that suppose there is more than one subgroup. So for of order m inside the cyclic group G of order n. Now my question is, how many subgroups of order m do you have inside a cyclic group? Is it unique or do you have more than one number of subgroups? So that is the next question, the uniqueness of say H. So we'll come to those questions in the next videos. Yeah.